Hello, myself Dr. Shaila Dinkar Apte. I am generating this video for chapter number 2 of Signals and Systems published by Cambridge University Press. This book is published by me. So we'll continue with the properties of continuous time and discrete time signals. We'll discuss following properties. The symmetry property, that means whether the signal is even signal or the odd signal. Second property is periodicity, whether the signal is periodic or aperiodic. Causality, if the signal is causal or anti-causal. And predictability means if the signal is deterministic or it is random signal. So we'll first continue with even and odd signals. The signal is said to be even if it is having even symmetry. That means if the signal that is existing for negative values of t is same as that existing for positive values of t. So this is for the even signal. You consider a rect signal wherein it is equal to 1 between 0 to t by 2 and it is equal to 1 again between 0 to minus t by 2. So for positive as well as negative values, the value is equal to 1. So this means that if you take the y-axis and you fold the signal around y-axis, you will find that it exhibits the symmetry about the y-axis. So if it exhibits the symmetry, the signal will be called as the even signal. So if it is odd signal, what will happen? The signal will exhibit anti-symmetry. So with respect to this y-axis, on the positive side, the signal is having positive value and on the negative side, the signal has negative value. So it is anti-symmetric. So you say that the signal is odd signal. Properties of even and odd signals. So if you consider that there are two even signals and if you take the product of these two even signals, the signal will have to be always even. Similarly, the product of two odd quantities will also be even. If it is a product of even and odd, then the signal will be odd. The cosine function is even and sine function is odd, as you can understand from the diagram of the sine and the cosine plots, right? So if you have the square terms in t, the corresponding function will be even. If you have the odd functions of t, the signal will be odd. Further properties of even and odd signals. Consider, for example, xt is equal to any function of t, let us say here sin t, and you take the square. So if the function contains the square term, it has to be even. If you consider the product of two odd functions, still it is an even function. So if you consider sin t into sine of 2t maybe, then it will be even function. If you consider sin t into cos t, it will be odd function. Now if you want to find out, suppose the signal contains two terms and if you want to find out which term is even and which term is odd, then you need to expand this bracket. So you will have to write xt is equal to t square cos t plus t square sin t and then find out which of these terms is even and which term is odd. So in this case, t square cos t is even, t square sin t will be odd. Now consider the dt domain. Now what you are supposed to do, what is the test? You will have to fold the signal around the amplitude axis and examine the symmetry or the antisymmetry. So in this particular case, the signal is defined between -2 to +2. So if you fold around this amplitude axis, you will find that the signal is having symmetry. So this signal is even, and in this case the signal is odd. As you can see, the signal exhibits antisymmetry. Now in this particular case, the signal exists between 1 to 5 only. Below 0 and for n is equal to -1, -2, etc., it is 0. So it is not existing at all on the negative side. So if you take the symmetry around 0, the symmetry does not exist. So you will say that the corresponding signal is neither even nor odd. So if it is having anti-symmetry, you will say that it is odd. If it is having perfect symmetry, you will say that it is even. But in this case, it is not defined at all at 0 and below 0. So if you fold at this particular axis n is equal to 0, you will find that it is neither symmetric nor antisymmetric because the signal is not defined at all below this. Now, what is the significance? The significance is when we are taking the convolution, in the convolution, the first step is to take the mirror image of the signal. So, when you take the mirror image, if you have understood or if you are familiar with the fact that the signal is symmetric or antisymmetric, or the signal is even or odd, then you can directly take the mirror image. The next property is periodic and aperiodic signals. The signal is said to be periodic if it repeats after some particular time t. So, the period will be normally denoted by capital T. So, it should be such that x of t plus capital T is equal to xt. It is satisfied for all values of t. In that case, capital T will be called as the period. So, in case you consider some sine function, so sine of 2 pi f t, and suppose if you want to say that this is equal to cos of 2 pi f t, then 2 pi f into capital T must be equal to 1, that means t is equal to 1 upon f. So, it is periodic with period equal to capital T. So, if you consider all analog cosine and sine functions, all these are periodic with period equal to 1 upon f. Now, whether this particular capital T is rational or irrational, it has nothing to do with that. In analog domain, it is always periodic, whether the corresponding period is rational or whether the corresponding period is irrational. It has nothing to do with the rationality. So, continuous time cosine and sine function is always periodic. You remember this. Why? Because even though it is some t is equal to 2 pi by 3, it is defined and I can say that after this particular period the signal is periodic. Now, what happens in dt domain? Let us see. Now, examples of periodicity in case of dt signals. Now, in this case, the corresponding signal repeats after every 2 samples, so the period is equal to 2. Now, in this case, it is repeating after 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. So, capital N is equal to 10 in this case. Now, consider this particular case. In this case, the signal seems to repeat between minus 1 to 1, between minus 2 to minus 1, whatever is there, same is between 1 to 2, 3 to 4 and so on. But at the center, it is existing and it is equal to minus 1 between minus 0.5 to plus 0.5. This makes the signal aperiodic. Okay. So, a signal, if it is periodic and if it is existing between minus infinity to plus infinity, then the signal will have to be called as a power signal. So, we will consider it later on. But sometimes what happens is the signal may not exist between minus infinity to infinity, but the signal may exist only for a finite duration, and over this finite duration the signal will be periodic. In this case, we relax the definition of periodicity condition and we say that the signal will be treated as periodic if it is periodic over the corresponding finite duration for which it is defined. So, it is not strictly necessary that the signal must be existing from minus infinity to infinity and it should be periodic over the entire interval. It is not necessary. Signal may be available only during the finite duration, still it will be considered as periodic. Now, consider the periodicity of DT signals. Let us consider the analog signal with 10 Hz frequency and it is sampled at sampling frequency of 30 Hz. Now, in this case, this is obeying the sampling theorem because the corresponding sampling frequency must be equal to greater than or equal to twice W, where W is the bandwidth. In this case, bandwidth is 10. So, 20 Hz is the minimum requirement, and now when we are sampling with f is equal to 30 Hz, we are obeying sampling theorem. Now, in this case, what we will have to do? Suppose we consider the 10 Hz signal. Then what is the digital frequency? Digital frequency will be 2 pi fn into capital T, where capital T is 1 upon 30. So, how much it comes to? It comes to 1 by 3. So, digital frequency comes to 1 by 3. Here I am considering a cos component. Xt is equal to a cos 2 pi f is 10 n 2 pi fn into capital T. What is capital T? Capital T is 1 upon fs, that is 1 upon 30. So you get it as 2 pi 1/3 n, and this 1/3 is equal to your digital frequency. 2 pi fn. I consider this as the digital frequency. This digital frequency is less than or equal to half, where half is the maximum digital frequency. So in this case, this is valid. And you will find that the corresponding period is 3 samples. That means after every 3 samples, the signal will repeat itself. Right. So this is case 1 for DT signals, wherein we are using the sampling theorem and we are obeying the sampling theorem. Now consider case 2. Now in this case, I am considering 10 Hz signal, but I am not obeying Nyquist criteria. I am sampling at 7.5 Hz, which is even less than 10 Hz. So what will be the digital frequency in this case? Just try to calculate. Xn is equal to a cos 2 pi. The frequency is 10 Hz, and divided by capital multiplied by capital T means it is divided by Fs. It is 7.5. So it comes to 2 pi 4 by 3 n. Now what is 4 by 3 into 2? It becomes 8 by 3 pi n. 8 by 3 pi n can be written as 2 pi plus 2 by 3, 2 by 3 pi n, which is same as 2 by 3 pi n. Why? Because cos of 2 pi plus anything is same as cos pi. So what you can say is 2 pi n into 1 upon 3. So 1 upon 3 is again your digital frequency. So in this case also the digital frequency is 1 by 3. But in this case we have not obeyed sampling theorem. The corresponding frequency 10 Hz will be aliased in this case. Now let us see how. So this is the graph, shows how analog frequency is converted in the digital domain. The maximum digital frequency is equal to half. This I have told you during chapter number 1 only. So let us consider sampling frequency as 7.5 Hz. So when it is 7.5 Hz, Fs by 2, that is the Nyquist frequency, becomes 3.75 Hz, and this 10 Hz goes above this 7.5 Hz. So this 10 Hz will then be aliased as this 2.5 Hz, because this particular line will fold back onto this original line, as we understand in the fold back effect. So this particular line folds back onto this particular line. So this frequency of 10 Hz is aliased as 2.5 Hz, and again what is the digital frequency? 1 by 3. So even though the digital frequency is 1 by 3, the analog frequencies are different if the sampling frequency is different. So one must know what is the sampling frequency in order that the corresponding analog frequency can be recovered. So when we say that you are at the transmitter end and let us say I am at the receiver end, the transmitter and receiver, they must be friendly. That means transmitter must be telling the receiver that I am sampling at f is equal to 7.5 Hz, right? Or I am sampling at 30 Hz. So this sampling frequency must be known at the receiver end. Then only the receiver can properly receive the corresponding analog frequency in the means after the digital frequency is received, the receiver can extract the analog frequency provided the sampling frequency is known to it. And now consider the sampling frequency as 30 Hz. If the sampling frequency is 30 Hz, 10 Hz comes here, that is below Nyquist frequency. So it will be directly obeying this linear law, and 10 Hz will be directly converted to 1 by 3 Hz in the digital domain. So in this case again no change in the phase. For 10 Hz with 7.5 Hz sampling frequency, also there was no change in the phase. Now periodicity of DT sinusoids, I am considering case number 3. Now in this case what variation I am doing? I am considering the analog frequency as the irrational number. Let us say that analog frequency is 10 upon pi. In analog domain, even though the frequency is 10 upon pi, still the signal is periodic. But what will happen in the digital domain now? So if I put f equal to 10 divided by pi, sampling frequency is 30 Hz. So what will happen? A cos 2 by 3 n. Now if the signal is represented as a cos 2 by 3n, you are supposed to compare it to pi fn. So what will be f? Compare it with 2 pi fn. 2 by 3n is compared with 2 pi fn. So what will be f? F is equal to 1 upon 3 pi. But this f is the digital frequency, and if this digital frequency is not the ratio of two integers, that means if it is not rational, then the corresponding discrete time sinusoid is not periodic. So when we convert analog sinusoid to DT sinusoid is not periodic if DT signal does not contain integer number of samples in each sinusoid. So in each period of the sine wave, there must be some integral number of samples present. So if it is not so, what will happen? The signal will not be periodic. This is very simple to understand. So what is the periodicity properties of TT signals? What it indicates? See, suppose initially we are considering 10 Hz signal and sampling it at 30 Hz, then the corresponding digital frequency is 1 by 3. So you can say the period is 3 in the digital domain. But if I now change the analog frequency to 11 Hz, the corresponding sampling frequency again 30 Hz, I will get f equal to 11 upon 30. So in this case, 30 is the period in the digital domain. So if you change the analog frequency by a little amount, the corresponding digital frequency changes drastically or by a larger amount. Also, a small change in the sampling frequency can result in a large change in the fundamental frequency in the DT domain. So, say for example, fs now becomes 31. So, f is 30 upon 31. So, now 31 is the period rather than 3. In the earlier case, when it was 10 divided by 30, I got f as 1 by 3. So, period is 3. Now, here it is 10 by 31. So, the period becomes 31. So, period changes drastically in the digital domain in this case. Significance of periodicity. So why we want to analyze this periodicity? So if the signal is periodic, normally what will happen is it will repeat itself from minus infinity to plus infinity. That means it will exist over infinite duration. That means the signal will have to be a power signal. The total energy is infinite, and if the average power is finite, it becomes a power signal. So if you consider the power over one cycle of the signal, then it is finite. So we say that we can use power spectral density to analyze it in the frequency domain. But if the signal is aperiodic and if it is existing only over finite duration, its energy will be finite. So the signal will be an energy signal, and we can use energy spectral density to find the frequency analysis of the signal. So in this case, the analysis for power signals and energy signals will be different. We will come to it later on when we consider power spectral density and energy spectral density. Another property of signals is causality. Causal and anti-causal signals. Causality means the signal is existing only after t equal to 0, and it is not existing for t less than 0. But if it is existing also for t less than 0, it will be called as the left-handed signal. So right-handed signal and left-handed signal, it has the literal meaning. So if the signal is existing on the right hand side of t equal to 0, we say that it is right-handed signal. If it exists on the left hand side of t equal to 0, we say it is left-handed signal. And if it is existing on both sides, we say that it is neither right-handed nor left-handed. Left-handed signal is also called as anti-causal signal, and right-handed signal will be called as causal signal. Why this is so? Because when I am collecting the samples from t is equal to 0 in continuous time signal, or from n is equal to 0 on in case of the discrete time signal, then we are collecting the samples in real time. So it will be called as real time signal. But when we have signal values available for negative values of time, means it has the memory. So in this case, we will say that it is the offline signal. So that is the significance of the causality. Now when we come to the causal system, you will understand that our body of our uh, mm, system, human being, is a causal system. We'll explain it later on. So this is the example of continuous time signal. Now in this case, if you define what is ut plus 2, ut plus 2 means it is existing for all t greater than or equal to minus 2. U of t minus 2 exists for t greater than or equal to 2. That means signal exists for t greater than 2. It also exists uh, for all t greater than or equal to minus 2. So from minus 2 to plus 2 the signal is existing, that means it is both sided signal. Similarly, this discrete time signal, it exists from minus 2 to plus 2 again. So this is again anti-causal, or it is existing for both sides of the n equal to 0 in this case. Now there is another classification of the signals. Signals can also classify, you can also classify the signals as deterministic or random. Now what is the meaning of deterministic? In deterministic, we have to consider what is the meaning of determine. You can determine the sample at any time t, then it is called a deterministic signal. Deterministic signal means there is no uncertainty, or there is certainty in the value of the signal at any time t. So we can specify the value of the signal at any time t by writing down a mathematical expression. So if you can write down the mathematical expression for the signal, it is deterministic signal. But in case of random signals, you cannot directly put down any equation to represent the signal, and in that case you cannot determine the probability. What will be the probable value at a particular time t? You do not know. So there is no predictability. In that case, you say that there is some random component in the signal, and the signal is treated as the random signal. For example, the speech signal. So that is why how this particular research in the speech goes on. It is like a huge elephant at the center, and it is surrounded by number of blind persons. So the persons are blind. So how they describe? They touch the elephant. If I touch the tail of the elephant, I will say that elephant is like a tail. If I touch the ear of the elephant, I will say that the elephant is like the ear, like its ear. Suppose I touch the feet, then I will say it is like the feet. So because I am blind. So this is what happens in case when we try to analyze the speech signal, because it is like the elephant, the properties cannot be understood. Because of the randomness, what happens is you cannot grab the properties of the signal, and in that case what you do? You concentrate on certain properties and then you say that the signal can be described using these properties. But this is not true in the true sense, right? Now, what is physical significance of deterministic and random signals? For a deterministic signal, the next samples can be easily calculated. Now, when we want to calculate the statistical properties like mean, variance, standard deviation, all these things can be calculated for the deterministic signal, because we can directly use the formula for the mean, variance, etc. Now, in case when the signal is random signal, what formula you will write for calculation of mean and variance and so on? You cannot calculate. So in that case, what you will have to do? You will have to fit certain standard probability distribution function to the signal. So you will have to find out the histogram of the signal and find out whether the histogram is similar to a particular probability distribution function. If yes, then what I can do is I can use the corresponding formulae for that standard probability distribution function for the calculation of mean, standard deviation and so on. So I can calculate all statistical properties. In the sense, I will have to say that I will not calculate, I will estimate. So we are doing the estimate of the statistical properties. For research for random signals, as I have told you, it is like the blind people describing the elephant. Thank you so much.